Hello everyone, thank you for tuning in to my talk. My name is Noor and today I will be presenting our QuickSilver framework for modeling and parameterized verification for distributed agreement-based systems. This is joint work with Christopher Wagner, Swen Jacobs, Milind Kulkarni and Rupsha Samanta. Now, most distributed applications are built on common distributed services such as data stores, caches, locks, and ledgers, which in turn often rely on some notion of distributed agreement to perform their higher level functions. Processes may need to agree on a leader, on members of a group, on owners of locks, and so on. For instance, some of the highly popular distributed services such as Chubby, Redis Raft, Zookeeper, and Cassandra are examples of what we call distributed agreement-based systems because they're built on top of agreement protocols like Paxos, Raft, and the Zookeeper Atomic Broadcast Protocol. And because these agreement protocols are fundamental building blocks, there have been a lot of verification efforts that targets their implementations. And as a result, there are verified instances of all of these protocols. Since we are interested in verifying such agreement-based distributed systems, and that we want them to be correct for any number of processes, this really called for parameterized verification. Now, the natural question to ask is, given that the design of such systems is inherently modular, can we then make sure that our verification approach itself is modular? Additionally, given all the efforts on verifying existing agreement protocols, can we then enable this modular verification by encapsulating the complexities of these agreement protocols into cleanly defined abstractions that we can then use when verifying these systems? And once we replace our agreement protocols with abstractions and arguably end up with a simpler system, can we then be more ambitious and try to consider fully automated verification? And since we're trying to do fully automated verification, this really called for using parameterized model checking, which is a problem of algorithmically verifying the correctness of systems parameterized by the number of processes, and is a well-known and decidable problem. Previous work in this domain focused on performing parameterized verification only modularly through deductive verification, where the user provides inductive invariants, or through model checking, where the emphasis is on full automation without much attention to abstractions or modularity. In this work, we tackle both dimensions through the QuickSilver framework for modeling and automated parameterized verification for distributed agreement-based systems. In particular, our contributions are as follows. First, we develop a modeling language called Mercury that has agreement primitives that one can use to abstract verified agreement protocols. Then, we show how one can perform efficient automated verification for systems modeled in Mercury via decidability and cutoff results. And finally, we implement our ideas and test them on an interesting set of benchmarks. Okay, so let me start by telling you about Mercury, our modeling language, and the two agreement primitives it supports. The first primitive is called partition, and it allows a set of participants to divide themselves into two groups. The partition primitive can be used to model agreement protocols like leader election, and it has the following syntax. It takes three parameters, an identifier, and a set of process identifiers indicating the participants, and a cardinality indicating the desired number of winners. Upon termination of agreement, the winning processes execute the win reaction, while the losing processes execute the lose reaction. Additionally, for an agreement round with identifier, say, elect, one can use the expressions elect.winAs and elect.loseAs to retrieve the set of winning and losing processes, respectively. This can be useful when you're trying to use these sets as participants for subsequent agreement rounds. The second primitive is called consensus, and it allows a set of participants, each proposing a value, to agree on a finite set of decided values. The consensus primitive can capture agreement protocols such as Paxos, and it has the following syntax. It takes four parameters, As before, it takes an identifier, a set of participants, and a cardinality indicating the desired number of decided values, and finally it takes a local variable from which the process can submit its proposal. Upon termination of agreement, all the processes execute a single reaction, and they can access the set of decided values using the this_var expression. And finally, one can use both agreement primitives to model agreement protocols such as Multipaxos and Raft, as we shall see next. Let's say that we want to model a distributed store where a programmer would want to store and manipulate their data on some server, and to do this in a reliable way, the programmer decides to replicate this data into multiple servers, and to keep things efficient, the programmer decides to additionally use a leader election protocol to elect one leader that can handle the client requests. Then, the leader can communicate with the replicas, agree on the command to be executed, and report back to the client. Let us now see how one would model such a system in Mercury using the agreement primitives we just discussed. First, we define a set of variables and communication actions, and then, starting at some initial location, we would want to elect one leader, and then the rest of the processes would act as replicas. In the leader location, the leader can then serve some of the client requests directly, for instance, read requests. Or, if the command needs to be replicated, the leader then moves to a new location and coordinates with the replicas. Once we agree on the command to replicate, then all processes go ahead and execute the agreed upon command, and the leader can then report back to the client. Finally, if the leader crashes, we would want to allow the replicas to go back to the initial location and elect a new leader. Then we can use the partition primitive to elect one leader from the set of all candidates, and use the consensus primitive to agree on which command to replicate and execute. The rest of the details are not important, but one can see the modularity of this distributed store model in Mercury. On a high level, a Mercury program consists of a set of variables, communication actions that can be broadcasts or rendezvous, and a set of locations with one initial location, and in each location there are a set of event handlers that can either be sends, receives, or internal handlers when the process wants to do internal computation, or one of the two agreement primitives we discussed. Finally, I would like to point out that our agreement primitives are sound. In particular, their global behavior is a sound over approximation of the behavior of any agreement protocol that has been verified with respect to agreement validity and termination, which are really standard correctness specifications for agreement protocols. Alright, now let's talk about verifying Mercury systems in an efficient automated way. So the parameterized model checking problem is defined as follows. Say you have some system M of n, which is a Mercury system composed of n identical copies of some process definition P. Then the problem of verifying that for any number of processes the system meets its specifications is called the parameterized model checking problem, and is a well-known and decidable problem. So in this work, we show that if a process is what we call phase compatible and the safety specifications is what we call permissible, then this problem actually becomes decidable. In the interest of time, I will refer you to the paper for more details, but on a high level, the decidability is obtained as follows. In previous work, we used the notion of well-structured transition systems to establish a decidable fragment in the Global Synchronization Protocols, or GSP, which is a theoretical model for distributed systems. And in this work, we extend the GSP model and its decidable fragment into a model we call Mercury core, and show that for any phase-compatible Mercury system, there exists a simulation equivalence with one in the decidable fragment of Mercury core. Going forward, we will need to talk about the local semantics of a Mercury program, which are best represented using a state transition system. For instance, the local semantics of our distributed store is as follows. The initial location candidate corresponds to an initial state candidate from which processes can perform an election and either win and go to the leader state or lose and go to the replica state. A leader can then perform a set of actions with the clients directly or switch to a state where they need to coordinate with the replicas on which command to replicate and execute, and so on. Finally, an example of a permissible safety specification for this system is in every reachable state, there is at most one leader. Okay, now that I've told you that the verification is decidable, let me tell you how we can actually make it practical. To do so, we use cutoff results. A cutoff result yields a specific number of processes such that the system is correct for any number of processes if and only if it is correct for that specific number of processes. This is nice because it reduces the parameterized verification problem to a verification problem of a system with a finite fixed number of processes. So really, the goal here is to make sure that we can find a small cutoff. To better understand our cutoff results, let's look at the following local semantics, where we have some initial state I and some state C that represents a critical section. From the initial state, a process performs a broadcast and moves to state 1, while all the receivers of that broadcast move to state 2. From state 1, that process can either go to the critical section or to some state 3 based on some local computations. Since C is a critical section, any global configuration where we have 2 or more processes in C is bad. Now, the minimum number of processes you would need to check the correctness of this system is in fact 2. The intuition here is that all path from the initial state to the critical state is what we call independent. So if a process were to reach C, it can do so without the help of other processes. A process can always send, and it can always do its own internal computations. Now, if the transitions are as follows, where we start by performing a partition that sends the winners to state 2 and the losers to state 1, then the minimum number of processes that you would need to check the correctness of this system is in fact 4. This is because in order for processes to advance from the initial state to the critical state, 2 processes have to win the partition, causing the cutoff to grow. In essence, we develop a set of cutoff amenability conditions that one can check on the local semantics to rule out such scenarios. So in particular, we capture systems where the minimum number of processes needed to trigger an M process error is in fact exactly M. Finally, let me quickly highlight some of our evaluation results. So QuickSilver proceeds as follows. Starting with some Mercury program and a set of safety specifications, we build the local semantics and we check if such local semantics are phase compatible. If it's not, then we return some feedback, and if it is, we check if they are also cutoff amenable. Again, if they're not, we return some feedback, and otherwise we compute the cutoff and check the safety of the system for that cutoff number of processes. If it's not safe, we return an error trace, and otherwise we are done. We tested our approach using the set of agreement-based systems listed here. For instance, consortium is a system where a set of actors want to reach the decision by delegating it to a subset of elected, trusted actors. Another example is robotics motion planning, where a set of robots coordinate to avoid obstacles and collisions. And the highlights are as follows. The cutoff for all of these systems were 5 or less processes, meaning that we are able to compute a small cutoff, and the time it takes to do fully automated verification for the most complex system was under 12 minutes. In conclusion, we developed a modeling language for agreement-based systems, a fully automated, efficient approach to verify systems modeled in this language, and an implementation of our ideas. Thank you.